Hello, it's Stat 135, Lecture 22. Great job on the midterm. You're done with that. You should really go to the beach because there's no lab today, there's no homework due next week, there's no quiz 3 next Friday. Just smooth sailing till after the spring break, and then we'll hit it with here are the following post-midterm topics. We're going to do parametric paired two-sample t-test, chi-square test, non-parametric two-sample t-test, analysis of variance, regression, both simple and multiple, and also Bayesian statistics. So still lots to do, but we're done with the midterm. Yahoo! So today we're going to do a paired two-sample t-test, paired and unpaired tests in R. And then we'll start looking at section 9.5, in particular, the multinomial distribution and chi-square test. So comparing paired samples, we wish to estimate the difference in population means, but in paired studies, we can no longer assume our samples are from paired populations. So we're going to have x1 to xn IID, sample mean mu x, variance sigma squared x, y1 to yn IID, sample mean mu y, variance sigma squared y. So these xi, yi's are IID pairs. The covariance of xi, yj is 0 if I is not equal to j, since in that case they're independent. Okay, and xi, yi, the covariance, which we'll write as sigma xy, is just the definition of covariance is the correlation coefficient of x and y, sigma x, sigma y. So we have the difference of xi, yi, call that di. The expectation of di is then mu x minus mu y, and the variance, so the variance doesn't distribute across the xi, yi's because they're dependent on one another, so we have to introduce a minus 2 covariance xi, yi. We have minus because of that minus in front of the yi. So, so now for large n, the sample mean d bar, it's approximately normal by the CLT, and we have that is approximately normal mu x minus mu y, and 1 over n sigma x squared sigma y squared minus 2 sigma xy. So notice that if xy are positively correlated, in other words, that covariance term is positive, then the variance of d bar is less than the variance of x bar minus y bar when x and y are independent. So in this case, we say that the paired case is more efficient. This means that the SE of d bar will be smaller than the SE of x bar minus y bar if your test data is unpaired. So, and of course this will mean, since the SE is smaller, that means that your test statistic will be larger, and so you're more likely to reject a null for paired data. And this is good if the alternative is true, of course. So now on to paired t-test. So we have our difference here, which is normal mu d, sigma squared d, and generally sigma squared d is unknown. So when we look at this ratio, d bar minus mu d, sorry, I should say, yeah, mu d, okay, standard error of d bar. This is a t distribution with n minus 1 degrees of freedom, just as usual. And so by duality of hypothesis testing and confidence intervals, the test with level alpha with null that mu d is 0, alternative mu d is not 0, it has a rejection region. D bar is greater than t Tn minus 1 alpha over 2 SD bar, or equivalently we reject if the true population mean for D is not in the written 1 minus alpha 100% CI for mu D. So then we did a in-class exercise to see how this all works. So we have, so I gave you some data here, and I'm first going to just examine this data. So I'm going to tidy it up so I can make a bar plot. And when I make this, I can examine the normality assumption, and it doesn't look very much like a straight line. I can also see that the SDs are different, so I probably would not do a parametric test here. I would do a non-parametric test called a Mann-Whitney test, which we'll do after spring break, actually. So let's do a, but let's ignore those difficulties right now, and we're going to do an unpaired test. So the SDs are different, so we have this complicated formula for the degrees of freedom. Here's how I code it in R, and so I get a test statistic which is t distribution with 15 degrees of freedom. I can find then the p-value and see that it's less than 0.01, so I reject the null. Now we could do the same data set but treat it as a paired test, and really all I have to say about it, just notice that now the t-value is bigger because the SE is smaller, as we said above, because apparently this data here is positively correlated. So so we'll get an even smaller p-value, and the efficiency is less than 1. So finally, we're just warming up to section 9.5. I just wanted to give a brief introduction to the multinomial distribution, but really just in terms of the binomial distribution. But I'll present the binomial distribution in a way that it'll be obvious how it generalizes. So binomial random variables is the sum of n independent Bernoulli p random variables, and a Bernoulli p random variable has two outcomes or cells. Let P1 be the probability of outcome 1, P2 the probability of outcome 2. If you have n trials, what's the chance of getting x1 of outcome 1, x2 of outcome 2, where x1 plus x2 is n? So the answer to this is exactly the binomial formula, which you can write as n choose x1, x2, P1 to the x1 power, P2 to the x2 power. So for example, if you have 2 red and 7 green marbles and you pick 3 marbles with replacement, obviously P1 then is 2 over 9 and P2 is 7 over 9. So the chance that you get RRG is P1 squared P2. In other words, 2 over 9 squared, 7 over 9. And but there's no reason to just have that ordering of 2 R's and 1 G. There's in fact 3 factorial over 2 factorial, 1 factorial reorderings. So that's just binomial formula. Now, let's think about this in terms of chi-squared. So in n trials, we observe, let's say, x1 of outcome 1 and x2 of outcome 2. Now, because the cells are binomial, you would expect NP1 of outcome 1 and NP2 of outcome 2. And the chi-square test is defined as summing over the number of cells going horizontally. So it's I equals 1 to 2 in this case. There are 2 cells, there are 2 outcomes. So it's OI minus EI squared over EI. And so I've written this out here. We have two terms, and these terms are dependent because x1 and x2 add up to a fixed constant n. If you do some algebra, you can actually see that you can rewrite this as x1 minus np1 squared over np1 q1. So we've gotten rid of the second term in the sum, and I've introduced a q1 in the denominator. And so this is pretty clearly z squared as n goes to infinity, which is a chi-squared with 1 degree of freedom. And this is since x1 is binomial np1, which is approximately normal np1 and p1q1. So we'll do this next time for the multinomial case, where we have more than two outcomes or cells, and we'll see that our chi-square test statistic will be a chi-squared with the number of cells minus 1. Have a great weekend, and I'll see you on Monday.